Hello, and welcome to PV Rocket Solar Photovoltaic Design Software. This is a quick start video for the calculations program to try to give you a minimum amount of information necessary to go through the program quickly and accurately and get you good results first time. When you first install the software, you'll find two ways of accessing it. There's a tab called PV Rocket and gives you access to the ribbon, and on the add-ins tab there's a pane of PV Rocket commands, and I actually prefer the add-ins tab because it more easily conveys the linear nature of the program. You define one box, you answer one box information at a time to define your solar PV system, and then get the assistance of PV Rocket in engineering it. If you use the tab, you might get confused about where to enter at, although they are tagged with numbers. And if you start at number 8, it doesn't matter. It will enter into number 1 because it knows you haven't done that yet. So let's go ahead and get started. I'm going to use the add-ins tab and click the calculations. And the first thing you do is every time you start AutoCAD, you have to sign in to internet access to have your license, your key checked that it's either a free trial or that you've paid for it. This is a warning that comes up about the limitations of the program and what it will design and what it will do. We have a limited amount of error checking, but I'll talk about that later. You hit accept on that. It only shows up on new projects. And then there's an end user license agreement that you have to accept. This only shows up the first time you use the software and whenever you update the software. And you check that, and here's our actual equipment definition box. So here is modules on the left, here is inverters on the right, and if we had what the National Electric Code calls a DC to DC converter, otherwise known as an optimizer, if we had that, that box would be defined over here. We have PV1 for the module and GT1 for the inverter, which stands for grid tie. So I'm going to pull down the manufacturer. It says unassigned. And the first thing you notice is these little lines differentiating areas. Right here it says local library is above and default library is below. The first time you use it, you don't have a local library, so there's nothing there. We'll talk about more what the local library is for in the longer video. But for now, let's go ahead and pull down a Canadian Solar, and let's pull down, doesn't really matter, this is just a sample project. Let's pull down a 365. So you noticed it populate all the data from the default library. You need to vet this information and make sure that it's accurate. PV Rocket has not vetted it, and the manufacturer has not looked at it. We didn't get it directly from the manufacturer. We got it from a third-party website from the government, California Energy Commission website. So check this. The longer video will show you how to edit it and make sure that it's right. And as you use the program, here, let me show you real quick. So I pulled down the manufacturer again, and you can see that the Canadian Solar got imported into the local library and all the models with it just because I added one. So as you use the software for a week, a month, or something, all your most common used equipment will be in the local library automatically. And that's one of the real benefits of it, is that you can vet each model individually and know that it's right and move forward with assurance. So let's go ahead and define an inverter also. I'm going to pull down a Selectria PVI 60TL. And now that we've defined grid tie 1, we have access to be able to define grid tie 2. And there's really no limit on how many inverters or how many modules you have. So I'm going to pull down, now that Selectria has been imported to the local library, I'm going to pull that down and import, or it's already imported, but I'm going to select a 50TL for grid tie 2. And that's really what this box is about. I'm going to hit next, and this is connection data for your specific project. So I'm going to put some data in here for the local area. I'm going to go ahead and select voltage drop required and say a maximum of 2%. We're going to get an error, a warning box later, and I'll explain why. But I'm going to go ahead and check it for now. Most inverters are transformerless now. I'm going to say we're line side at 600 amps. The main switchboard is NEMA 3R outdoor, 3-phase, and 480 volt. And I'm going to go ahead and hit next. Now, we haven't strung anything. I'm going to pause here and say that I'm running AutoCAD 2020, and it's a clean drawing that is empty. First time use. So we haven't strung anything. It has no idea how many inverters there are. So I'm going to hit add inverters. And for the sake of this project, I'm going to say we have 7 and hit save. So it populated 7 inverters out here for me. Let's assume that we're in the middle of a field, a ground mount fixed array, and this is defining the AC output of the inverter. So let's say that we're racked along the back of the array, so we're exterior, not roof, not interior, and not trenched. This is all temperature derating information is what we're giving it here. Let's say we're copper, and this line up here is the phase conductors. This line is the neutral conductor. So I'm going to say it's copper also, and I'm going to say it's derated. What we mean by that is Article 705 allows the neutral to be sized to match the ground and not the phase conductors. If you wanted to match the phase conductors, you could click full size for that. And none is kind of an obsolete holdover to the beginning days of PV Rocket. A long time ago, some of the inverters didn't have a neutral or need one. Current carrying conductors in the conduit, I'm going to select 3. And now I've completely defined inverter 1. I'm going to go ahead and hit copy first to all and populate all 7. You'll find that all over the place. Handy little thing to avoid repetition. I want to make inverter 7 different. Right here on the model number it says PVI 60. I'm going to pull down this grid tie 1 and turn that to grid tie 2, and you can see that it turned to PVI 50. This is just a little visual reminder that we give you so that you don't have to write too much down. Which one did I make 50? Which one did I make 60? I don't know if it was a grid tie 1 or 2. I'm confused. That'll help reinforce that. So now I've defined everything. I'm going to hit next here. Now, some people call this an AC combiner panel, sometimes an aggregation panel. This is user definable, so you can put anything in there that you want. I'm going to hit add one, and notice it behaves a little bit different than the inverter did. It didn't ask you how many, it just popped one in there. Sometimes on inverters we do projects that have 30 inverters, and we don't want you to have to hit add an inverter 30 times, so we do that for you. But on these AC aggregation panels, there's usually just a few. So I'm going to add and make it 3. So up here at the top, this is aggregation panel 1. This is where you define what is connected into panel 1. So I'm going to say that panel 1 collects inverter 1 through 4. I'm going to say panel 2 collects inverter 5 and 6. And I'm going to say panel 3 collects inverter 7. Then I'm going to say panel 1 goes into panel 2. So before I clicked on inverter 1 and then I held the shift key and clicked inverter 4. Now I'm going to hold the control key and click panel 1 there. So panel 1 goes into panel 2. Panel 2 goes into panel 3. So this is what is connected into these panels. Now stop here for a second and realize that panel 3 is not connected anywhere. This is how we tell PV Rocket that panel 3 is the one that's going into the main switchboard. 1 and only 1 panel can connect into the switchboard. Now we do handle multiple points of interconnection, but that's another video. Now down here is the outputs, just like the inverter was. So in this case, I'm going to say trenched, and I'm going to switch to aluminum, and then the neutral I'm going to say is derated and switch to aluminum. I'm going to say the panel is 3-phase and outdoor, and the output circuit has 3 current carrying conductors in the conduit. Now I'm going to hit copy first to all and populate that all through. I'll hit next. Now this is what's connected between the array and the main switchboard. You can see right here it says array and main switchboard, and it's going to assume a fuse disconnect all the time, every time, but you can delete that and you can change it and add things. So right now let's add a meter in here. So I come down here and select meter, and nothing happened. I did that on purpose because I want you to see this little reminder that popped up there. It reminds us to select our NEMA configuration. So I select NEMA 3R and hit meter. Now we added a meter in there. I want to change the order of this, so I select it and move it up on the list. So now we're going from the array, which is really AC combiner panel 3 output, to the meter, to a fuse disconnect, to the main switchboard. And that's the way this works. So I hit next. Now I get a warning box here. It's saying that I said voltage drop is required. Right here it's saying turning the voltage drop required to off. And the reason is that voltage drop and a lot of the other calcs are based on distance. And PV Rocket measures the distance from one inverter to the next, to combiner panel to main switchboard, right from your drawing. And like I said earlier, I'm starting from a blank empty drawing, so there's nothing to measure. So it can't be done. So this is the warning box I mentioned. I'm going to hit OK on that, and now I get a different warning box, and it says 240.4B is being employed. It's possible that 240.4B is being employed. It doesn't know for sure because not all the calculations are finished. But 240.4B says that the ampacity, the current carrying capacity of a feeder, can be below the circuit breaker protecting it under certain circumstances. And it's asking if it's okay with you that we use that. The default is already highlighted as yes. If you want to use fully rated feeders, you would click no here. So I'm going to click yes. We get a different warning here. It says that the system output current exceeds the service rating in violation of Article 705.12a. It'll let you do it. It's just a warning. We'll see. We'll look at that again more later. So I hit enter on that. Now this is the results page. It allows you to preview certain things. So if you had come through here and wanted to change something, so you went back and then you came forward again, it allows you to look at it before you hit print on everything. So I'm going to go ahead and hit print. The way we do that, we've got these buttons across the bottom. Some are grayed out because these are values, these are things that we can't do, like voltage drop. But the rest of them we can. So I'm going to hit print one at a time and then close. Now at this point, if you had a template drawing, you would be finished. Everything would be dropped in there, everything's great. But I started from a clean drawing, so look at the command line down there in the bottom left. It says select insertion point for system summary table. And it's waiting for me to click on the screen. So I'm going to click over here on the left, and notice that it inserted an insertion point. That's what we call an insertion point, system summary table. And then it dropped the system summary right onto that insertion point. To create the template, what you do is you take these insertion points and move them to any tab, paper space, model space, it doesn't matter, and then you can freeze them and ignore them like they're never there. And PV Rocket, when you go to print, will seek those out on any layer, frozen or not, any tab, any layout, any model space, and drop the output on there for you. So let's go ahead and continue. Now it's asking me for a feeder schedule location. And now it's asking me for some calculation locations. I got some labels populated, more calculations, one-line diagram equipment, and an equipment schedule. Now it's finished. And that's the heart of PV Rocket. That's your quick start video. I'm not going to stop because there's a couple things I want to show you. I want to show you how to get voltage drop done, and I want to show you the one-line diagram in detail. So let me zoom in here. These are dynamic blocks, and all the information that we've told it are populated here. And what we do is there's some manual work to be done here, and it's straight AutoCAD. PV Rocket is finished at this point, but with straight AutoCAD we got some work to do here. Eventually we anticipate doing a lot more of this for you than we are right now, but for right now we've really backburnered most of it. So let me show you. So right there I stretched the inverter up, and now what we have is this inverter has 3 MPPT trackers with 5 string inputs. So here's one with 5 inputs, and they were on top of each other. So I'm pulling them aside one by one and then working to stretch them and make the whole thing look right. Now that looks pretty good, but I'm going to go ahead and pull this one down and that one down and that one and make this a little bit tighter. There. Now, I'm a big fan of uniformity from inside the company and from one designer to the next. So I'm going to go to the PV Rocket tab and pull down Insert and Find. And there's 3 blocks left that we allow to be inserted. I'm going to pick Array Lines, Insert, and give it a location, and then close the insertion box. This is a dynamic box, and it's a little bit silly, dynamic block. It's a little bit silly to include, but I like the uniformity that it gives us. So everybody's drawings all look the same, and it looks the same inside one drawing. So I paused the recorder there for a second so I could do inverter 7 also. So let me point out to you a couple of things here. First of all, here's more insertion points that came in during the printing, and let's go ahead and freeze those now. So they're on PV Rocket insertion point layer, and I clicked freeze on that and they're gone. So notice that we only got 2 inverters even though we have 7. Inverter 2 matches inverter 1, inverter 3 matches inverter 1, and so because these labels are labeled like that, we don't need to print all of them, and that, you know, these are typical, so we don't print all of them. So let me start to finish off the one line, and what you do is you just kind of move things around. Again, straight AutoCAD. So I move it up in line, and now the way we do it is I make a straight hard connection. So this text is not necessary there anymore. It's just kind of a guide, especially if you have drafters involved in the company. Your designer could be moving on to something else now. So CB01, these are our interim devices is what I call them, the meter and the fuse disconnect that we had. And there's the main switchboard. So I'm going to move these off to the side. So CB01 goes to CB02. If you remember, this is CB02 and it's meant to come in right there. The input is always on the bottom half of the panel. So this top half, there's separate blocks actually because of limitations in AutoCAD. This is the way we had to do it. So there's one block for the top half and one block for the bottom half. So the top half is always inputs from inverters, and the bottom half is inputs from other combiners or outputs to things like monitoring equipment and such. And the reason for that is because there's not a label on this side. The label is over here on this side. And since there's not a label here, this is where you put things like feeders to the monitoring equipment. So I'm taking this text out. And there we have it. So now CB02 goes to CB03. And by the way, aggregation panels are by default abbreviated to CB for combiner box. It probably should be CP. That's customizable. Here, let me show you real quick. You pull down the PV Rocket tab and click Options, and it's right there. So CB02 goes to CB03, which is down here. Make the hard connection, get the text out. Whoops. Now this is where inverter 7 connects into, so I'm going to move that up like that. Now we're connecting up through the feeder schedule tags. This text right there is on a non-plot layer, so you don't have to worry about that. And we said it was line side, so we're going to connect in right there. Like that. So I didn't pay a whole lot of attention to how we're fitting this onto a sheet. There's more uniformity I could do, but I'm not going to nitpick my own work here for the video. But this is how it flows. Left to right, stretch things around, move it around, and get it taken care of. Okay? So there's a minimum that you need to know to get the one line out looking right. Now let's talk about voltage drop. Voltage drop, like I said, is measured from your drawing itself. So let's drop some blocks in so that it can measure those. Go to the Insert and Find command again, and let's drop an inverter panel and main switchboard block. You click on it, push Insert, click on the screen, give it a rotation, and close. So I'm going to, and this again is straight AutoCAD, I'm going to name the first one INV01 for inverter 1. I'm going to pause the recording and give us some more blocks. So now I've dropped all the panels in. Inverter 1, 2, 3, 4, 5, 6, and 7. CB01, 2, 3, and main switchboard. That's a minimum of what you need, and it gives you all the AC calcs. We haven't done the DC yet, and I'm going to leave that for the quick start video on stringing. So let's go up, and I pulled this down. We've completed all these, so now we can enter anywhere we want. Let's go into verify distances and see what the program PVRocket measured. So this is what it measured. I just threw these blocks in, no regard to anything. You can leave it like this. These are measured at right angles, assuming that we're on the roof or for some reason need to measure at right angles. If you want to measure straight lines, you could do that too, but these are measured at right angles. And you can come in here and change these values if that's what you want to do. The reason we put this box up there was one time I did a project where we had two panels side by side in plan view. So it measured them at 3 feet apart. But in reality, they were like 100 feet apart because one of them was on the wall of outside the building and the other one was on the roof of a 4 or 5 story building. And and it had to go through the building. It couldn't just drop straight down. There wasn't a straight chase, so it had to go over to a stairwell and then come down and then over. And so it ended up being kind of crazy, having to redo a lot of our calcs manually by hand, which is no fun. So we developed this box for that purpose. And a lot of people like this because then they could just drop, if they know they're real numbers, like maybe they used True Tape or something, they could drop those in. Now before I move on, I'm going to hit save on this because if I come through here again, I don't want to have to re-enter those values I just put in. I can hit remeasure and go back to AutoCAD numbers. I can clear that memory out and all kinds of things right there. So I hit next. We saw this warning last time. Now I'm into voltage drop box. So let's look at this CB01 to CB02. It's saying there's one run of 700. We leave it up to you to remember that this is aluminum. The voltage drop is 0.2% and the cost of the run is there. We do track costs. In the longer video, we'll show you how to customize that. Up here at the top, we haven't defined any trenching, so there's nothing there. We're estimating the cost of these 3 panels at just below $5,000. We didn't string it, so there's 0 cost there. And the total cost is the aggregation panels and these feeders. So the worst one that we came up with is inverter 4 down here. And that makes sense, intuitive sense, because the main switchboard is over here, goes to CB03, goes to CB02, goes to CB01, and then out to 3. So if I hit up on any one of these, I think that inverter 3 just changed. Up is conductor size. That's what we're changing, just to make that clear. So I saw this one change down to 0.9. So the ripple effects, these feeders up here are 0.2 and that's 0.1. This is for these segments only because those are for the main switch, for the main aggregation panels. But when you get down to the inverter, it's accumulative along its route. And that's why we have cost associated here, because it might be cheaper to move one of these up, or it might be cheaper to move one of these up and make 3 come into compliance down here, if that makes sense. We're getting some cutoff just a little bit that I hadn't noticed before, and we'll get that worked out. This one might be cut off because there's only one inverter. Yeah, I got some cutoff down here too. We'll look into it. So here's another save button. Another opportunity to not have to put this in to practice again. Those changes. So they're locked in now. So let's hit next. It's got the same warning we saw before. And now we got outputs that aren't grayed out anymore. So you can click on all of these. So that was fault current. So here's a fault current calculation. I advise you to be very careful about this. You really need to get the utility to give you the starting fault current at your switchboard before doing anything like this. But I'm going to say that the utility see, I would have got, if I got the utility AFC, it would be up here. And then I would say if it's at the transformer or at the meter. But that's blank. And so I'm going to have PV Rocket calculate it, which is dangerous. And that's one of the things that the warning said about at the start of the program. So length of the secondary for utility is 20 feet. How many parallel and what size? I don't want to get into that. I don't typically. I usually come down here and click on the conductor as aluminum and make PV Rocket help me with something that's valid and works for our service size. The conduit's usually PVC, and I hit print. I'm going to go ahead and just hit reprint on all this stuff down here. And it stops again. If we hadn't had the information in before, then it doesn't have the insertion points. Oh, and I meant to move our one line diagram that I worked on so hard out of the way. But what I really was aiming at was showing you the new feeder schedule. So notice the new feeder schedule. The old feeder schedule stopped at percent fill of conduit. Now the new feeder schedule has the distance, has the segment voltage drop into it, and the total voltage drop already. Now I just paused the recording and fixed my mess up where I should have moved my pretty one-line diagram out of the way. So this is the new one-line diagram, and it looks exactly like the same as the first one the first time. However, there's a available fault current tagged right into the diagram now that wasn't there before because we didn't have the distances. Like I said before, be very careful about that, but that gets populated into here. There's calculations over here of how we got that, shows the equations, shows all the numbers, and can be checked by anybody. Here's the voltage drop done segment by segment throughout the whole thing, and that is the Calcs program. Thank you for your time. Welcome to the Quick Start video of PV Rocket for Stringing program. Now I've just recorded the Quick Start video for Calculations program, and you'd think that we would start with stringing, but it's often at our company we're asked to do a interconnection drawing to get the utility moving forward first because they are the long lead time item. So we'll do a calculations run first and get a one-line diagram and something for the utility to look at and get started on, and then we'll fall back and work on stringing. So that's why we recorded them in the order that we did. So this is the one-line diagram that we came up with. I want to start by showing you something. We used a PVI 60 and a PVI 50 TL. And they have 3 trackers with 5 inputs. That's 15 strings. And I didn't even mention, but the system's not strung yet. So what it did was it assumed that all 15 strings are used. And up here, you notice it says 150 modules. What it did was it assumed 10 modules per string, just to get a number in there and moving forward. So let me erase this up here because this is where the one line is going to drop in at. But let me show you the first level of control that we have, and it's minor, and a lot of users don't even know that it's there and it works. But let me show you something. I'm going to pull down the Calcs. Let's see, I think it's up here on box 1. Yeah, there's a string calculator right here. And if I go into that and give it a maximum system voltage of 1000 and hit calculate, it'll tell me that 19 modules will fit and give me a maximum voltage of 970. I could also just manually change it and say 18 and calculate and get the voltage for 18 modules in a string. If I hit close on that and then hit enter and go through all the boxes back to the end, I can hit print one line and then go to where the insertion point is, and you have to see that other video to understand what I'm talking about. But it gives us 18 times 15 must be 270, so it gives us at least a right count on that. I'm not saying it's a big level of control, but it's something. So let's get into stringing this, and how do we actually tell it how many strings we have. Let's say there's not 15, let's say there's 12. Four strings per 3 trackers, that's 12. Let's start doing that. So up here is the inverter blocks that we just threw in during that video, that Calcs quick start. Let's throw in let's go to insert and find just like before and put in a module and say insert and give it a spot and then hit close. So this is our current module. We used to have a lot fancier. We still have a dynamic block that you can have access to, and I'll show you how to do that on the longer video. So the first thing that we do is highlight it and then type in block edit or bedit and hit enter, and then it says you want to edit the master module master, and you say yes. And then what we do is we stretch it down to the actual size of your module. And I like to stretch from both sides so that the attributes stay centered, but you don't have to do that because you're never going to see these attributes, especially on the final drawing. And like that. I'm going to hit close block editor and save changes. So now we're ready to go. I want to point out to you that if you want to change this block, you can. It's required to be called 2D ED module master, and it's required to be on layer $modules. And it's also required to have 3 attributes in it, like you just saw in that video or in that block editor. So let me pause the recorder and lay out our arrays. Okay, so I laid them all out and rotated some to the left and some to the right to show you some things about the way the stringing is done. Let's make one of them unique. So I laid out 18 modules, 12 strings of 18 modules each. Let's make inverter 3 unique. Let's make it, instead of 12 strings, let's make it 10 strings. And let's make string 7, 1, 2, 3, 4, 5, 6, 7. 15 modules. Now I think that makes a total array of 1,473 modules, and the typical array of each inverter has 216 modules except for inverter 3. It has what's left over. So let's go ahead and start the stringing program. Total array modules 1,473, 7 inverters. We'll do microinverters another video. Hit next. It takes a guess of 210 and puts the remainder on inverter 7. Let's change it to 216 and hit copy first all to bring that down, and then inverter 3. See how this modules remaining changed to -39? So it's saying we have an excess of 39 modules and need to take out 39. So 216 minus 39 is 177. And I press enter and the modules remaining goes to 0. So modules remaining is trying to help you get to your total modules of 1,473 that we told it. And that's what that goal is always doing. And hit next. So color coding, let's skip for now. That's another issue. strings per inverter, I said 12 strings, except for inverter 3 I said 10. Hit next. It's taking a guess. It says, okay, you told me that there's 216 modules on inverter 1 and has 12 strings, so I'm going to guess that there's 18 modules each. That's a good guess. I'm going to go to inverter 3, and this one's wrong. So it's 18 modules for all 10, so I'm going to go copy first to all. And then I said string 7 was only 15. See how the modules remaining is an excess of 3? So I took that down to 15, now I'm at 0. So all the rest of these should be good. So I'm going to hit skip to the end. Now we're into stringing. Now there's 3 ways to do it really. There's string by string, there's sequential, and then there's speedy strings. We can't use speedy strings because they rely on the color coding that we skipped. So let's go to inverter 3 and do string 2. So notice nothing's going on, nothing's happening here. I'm going to click out in the left click out away from the array. So I just did that. And I draw my mouse through there. And what it did was it counted them on the fly and then put the label in there. Inverter 3 string 2. Let's do string 3. And let's show you that it's counting. When it gets to 18, so one more, it drew the string in. Okay? Let's do string. I wonder if it'd let me do string 3 again. I don't want to try. Let's do string 4. Right here. Now, notice I can go backwards and forwards. Now let's say I start to mess up. Like this. Now I could go backwards and fix it, or I could come back around, and as soon as my cursor hits 6, it's going to assume that 7, 8, 9, 10, 11, 12, and 13 are wrong and take them out. So there it did that. So let me keep stringing string 4. Let's do string 5. Now let's say I wanted to go diagonally from here to that one up there. I don't know why, but let's say we did. I could pause the stringing by left clicking again. Now notice it's not counting anymore, but if I come up here and left click again to resume, it resumes. Okay? Trying to think of anything else I could show you. Now, the sequential button says it's going to start at string 1. Let's go ahead and string 1. Now the sequential button says it's going to string 6. Let's go ahead and do sequential and show you that. So just like that, you left click and put that in. Okay, and it works a lot like the other one, but it's ready for the next string always. So let's go ahead and do the next one, which is string 7, which only has 15 modules, and you see it counted that. So let's do a Control Z, which is undo. and take that 7 out. 6, 5, 4, 3, and let's put 3 back in. And there we go. You might have expected it to stop there, but it's really ready to move on to inverter 4. See? Inverter 4 string 1. So I'm going to go Control Z and Control Z just to show you how powerful. So it knew it knew we were back to string inverter 3 string 10. So I just hit escape and got out of that. And now I want to show you color coding. So we've already done all the boxes, so we can go straight into color coding by pressing up here on the ribbon, color code 3. And just like before, I can do it in any order. So I'm going to go inverter 2, inverter 1. Now it says sequential starts at inverter 3, so let's go ahead and do sequential. Inverter 3, 4, I made this one inverter 5 earlier. Inverter 6, and 7. These are all still okay, of course. I'm going to go skip back out to strings. So what is speedy strings? Let's do speedy select first. Notice I'm on inverter 1. Let's do speedy select on inverter 2. So I click there. This is inverter 2. I start to string that, and even though we came from the inverter 1 box, just like we did for inverter 3, well, we were at inverter 3 and strung inverter 3. So this time we were at inverter 1 and strung inverter 2. And using speedy select, it knew which inverter we were on from the color code. It picked that up from the color code. So I'm going to go and do all of these. And there we go. So now I'm going to do speedy copy. So it says, which one do you want to copy? And I say inverter 2. Now what it's doing is it's looking for arrays that are the same shape as inverter 2 and copying those to them. So I'm going to hit close. And see, it copied inverter 2 to inverter 1 and inverter 4. But it didn't, even though these are the same shape over here, they're rotated to the right, and so speedy strings doesn't pick them up. Speedy copy doesn't pick them up. So now let's do speedy strings. So I'm going to click the last box, stringing, because we've been through all those boxes before. And it says already strung for inverter 1, which is true. Let's do speedy strings. Speedy strings is the combination of speedy select and speedy copy. So I click on speedy strings, and notice I was on inverter 1, but it, just like speedy select, it knew I was doing inverter 5 from the color code. So let's go through here, and at the end you'll see that it goes straight in without asking to a speedy copy. Speedy copy asked, which one do you want to copy? Speedy strings knows we're in the middle of doing inverter 5. So it's assuming that we want to copy inverter 5. So right now it's copying inverter 5 over to 6 and 7, which it just did. There's 6 and there's 7. So now we're fully strung out. Now, let's go back and look at the one-line diagram and the voltage drop box. The one-line diagram, the insertion points are right here on frozen layers. The voltage drop box is empty because we had no strings before. So let me erase that and go into Calcs. And I'm going to go, do I go straight to the end? Let's go into distances. I was while we were paused, I cleared out memory on this. And so these are the new location memory distances for all this. Let's go next. And these are minimums. I cleared that memory out too while I was paused. Hit next. I get the same warning I did before about the system appears to be in excess, but I also, now that it's strung, I get a new warning that we didn't have before. The DC to AC ratio is not advisable. 1.31 may cause clipping. So PV Rocket doesn't do a whole bunch of error checking for you on the solar design. It's an AC, it's a construction document design tool, but we do what we can to help you. So just little warnings here and there. Have you looked at this? Did you look at that? This looks a little bit weird. But we don't stop you because we want to give you the flexibility needed to do a proper job. Because for all we know, you're going to go and hand adjust some things because of limitations in PV Rocket, because there's 100 ways of doing anything. So we're at the results again. I'm going to do DC voltage drop table, and I'm going to say print one line and hit close. So that it's still going through some calcs. So the DC voltage drop table now is populated. Inverter 1, 18 modules per string distance, the amps, wire size on it. By the way, the wire size, if you go to connection information, if you go to the connection information box, at the bottom down here it says DC conductor size and it's set to number 12. If we had had 10, that information would be in there. Minimum ground size, maximum copper size, maximum aluminum size, all that's there. So it's got voltage drop done, DC, volts maximum power. It's got a total expected length of DC runs. And let's look at the one-line diagram. Now, if you watched the calculations program, which I encourage you to, we only had inverter 1 and 7. Those were our unique inverters. And they assumed that we had a string for every input, so there was 15. Now look at this customization that's there, auto-populated. Now we have 12 strings of 18 modules, 216 count, and we can put those onto our inverter. Which, just like the Calcs program, let me show you how it's done. Now, in the Calcs program, I showed you array lines. Now, you see a problem here? You should. We've got 3 on tracker 1. Tracker 2 has all 5. And tracker 3 has 4. There's no way to get this array. How do you get this array? Is it in the block? the way we do it, there's a tag over here that we could change things, but I'm telling you that's not it. There's a little trickery here that we have to do. So I'm going to move the array lines off for a second. And I'm going to use this thing up here called separate DC array. And it on the help there it says separate divide the DC array. So I'm going to click on that. And it's asking me select the attribute or insertion circle. So I'm going to show you what that is. Select the attribute. So I want string 1, 2, 3, and 4 to go to this tracker. And the way I get the output, see I'm still on pick mode. The way I get the output is come pick one of the circles over there on the fuse. And it took those over there. So I'm going to hit enter to repeat the command and say 5, 6, 7, and 8 are on this tracker, and 9, 10, 11, and 12 are on this tracker. Okay, so I'm going to move that over there, this one to there, I'm doing this wrong. Now this empty array thing over here is still useful. Let's move it to the side for now. And move the 3 arrays out. And bring the strings down. And change it so that they only have 4. Let's just copy those strings while I'm sitting there to the other 2. And now let's connect the strings to their inputs. Like that. Now this is where the box comes in handy. Let's bring this box back. And make the boxes that are blank in here go away. So you select on it and pull this and change it to 0. And that cleaned it up. But now the box is taller. So we need to stretch this one back down the end. And now you have that. And see, what we needed was this array to be separated into separate smaller arrays so that we could miss fuses that are not being used. And that's what the separate DC array is for. Notice that inverter 3 is now a unique inverter. So it popped up with correct 10 strings. It remembered that that string 7 only had 15 modules, and it got the count right at 177. So that's why inverter 3 shows up. And over here on the panel, it says inverter 3, and it doesn't say matching inverter 1 anymore, because inverter 3 is now unique and needs to be connected up right there, like we showed you on the Calcs program. Really, the only thing I could think of to show you, that's the essentials minimum quick start video for stringing. The only other thing I wanted to show you is if you want to take away the color code, you want to use Speedy, so you color code, but you want to take it away. The best way to do that is not you're going to be tempted to come in here and change the properties, take away the color and stuff, but there's information here embedded that you should really take out. So there's a command in here called reset color code on the support functions tab, or if you're using the add-ins tab, it's on this pull down, reset color code, and you just draw a box around the array and it takes it out. So if you ever have to reset the color code, that's the command I want you to use. And that is the stringing program from PV Rocket. Thank you for your time. Hello, this is PV Rocket, and I've already recorded a quick start video for the calculations portion, and I've already recorded a quick start video for the stringing portion. Now I'm going to go back and go into depth box by box on the calculation. And I may not even need to do that on the stringing program, because the quick start video really, there's not much to that. But on the calculations program, there's a lot going on that I glossed over the first time, just trying to get you out there. So for instance, when we covered this box, I introduced the concept of a local library and a default library. And I said that the purpose of the local library is for you to fully vet the information from the manufacturers and get it into your local library and have a comfort level and make sure it's right and everything. So I'm going to show you how to do that. There's editing done through PV Rocket, and I'm going to introduce you to the concept of a third library. So let me right now develop more of a library here. Right now the only local library we have is Canadian Solar. So I'm going to pick some others that I have, that I know. Just random stuff. And every time I pick a model here, it's importing the entire all the manufacturer and all the models and everything into the local library. And I just realized I went completely alphabetical. Let me go back and pick some out of order. So now they're in the order that they were selected. So C before A, and they're out of order. So let's go back to Canadian Solar, and I think I started with a 365. And let's restore that as my selection set for PV1. Let me close this and point out that we have the default library and we have the local library, and we also have a project library, a third type of library. The project shows only, so the local library is for your company or your employee or your user, and like I said, it's fully vetted and everything, but it's the library that has multiple models, multiple manufacturers, has everything that your company uses. And the project library only has what was selected for this job. So in what we just did, we created a project library without even trying. We created a project library that has a Canadian Solar 365 in it. And that's all it's got. The local library has those, what did I pick out? 10? 10 manufacturers, and I probably picked up, what, 100 models in it? And the default library comes from PV Rocket. Well, it doesn't come from PV Rocket, but it comes with PV Rocket. It comes from a manufacturers, no, not manufacturers, I'm sorry, a California Energy Commission website. So let me pause here, pause the recording, and show you what the files actually look like. Okay, so this is this is the default library. And as you can see, it's coded. It's hard-coded into machine language. There are tens of thousands of modules in here. And we needed to get it in so that when you select on those things, the response is immediate. And if we left it in here's the next file, which is your local library. And if we left it in this format that could be read, when we selected on those things, it was literally minutes compiling the information and bringing it up so that you could look at it. So we couldn't do that. So it's hard-coded into the PV Rocket. So this is your local, what we call a local library. Here's the manufacturer, Canadian Solar, and then here's the model numbers, and this is all very readable. You could figure out what this is. The STC conditions current maximum power point is 5.93 if you're looking at model 170 PE, right? So it's all readable. And if I scroll down here, I get to the next manufacturer, A-Green Technology, and there's its models. And here's Alpha Solar, and there's its models. And this is all very readable. And the job specific library, look at this. It's got one. And it's also readable. Canadian Solar 260. Oh, I thought I picked a 365. I must have gone back and picked a 265 accidentally. And there it is. So the local library, I've already gone over what its attribute, what its the reason for having it. You can fully vet everything, and it doesn't have to be just for one person. You can put it on a server, and it can handle multiple users. Now that's not fully tested, because here at our company we used to do it that way, but more than 5 years ago we got so spread out and we had people working from remote offices, and they were connected in a variety of ways through the internet, VPN connection, this connection, that connection, and some of them were just too slow and we couldn't function like that. So long time ago we moved the local library to each and every person's local C drive to take care of that lag in internet connection speeds. But but I still believe that function works, that you can have multiple users on the same local library. And then the project library is a path that's relative to the job number. So if you have a storage system where you have a job number for a directory as a job number and everything, then it gets stored. So let's look at the options tab, and right here it says plugin path and shows where the application plugins go. That's where the default library can be found. Then there's a relative job path. So the relative job path means, like I just said, you got a job that says 2020, job number 2193, and that's where the drawing file is. So it'll append, PV Rocket will append 2020/2193/Calcs/PV Rocket, and then we'll have the job specific library here, the project library, in that directory path, and it stays with the project file. And then the library path, the default is C support PV Rocket, and you could change that. You could put it on a server or anything like that, but those are the paths. So that all is background for what I'm about to show you. So when I pull this up, now notice I have a Canadian Solar 265, and I'm going to pull this down, and notice that they've been alphabetized now, and that's okay. What it did was it went and reordered the local library, but the job library still said Canadian Solar 265, and that's what we got. So that's the first thing to notice, is that um, that's how it's working. So let's say we go in and we don't want this to say 8.1 amps. The manufacturer says that it's 7.9 amps. And the VOC went up to 44.2. Now I'm going to hit close and reopen. So that's 7.9 and 44.2. So there they are, 7.9 and 44.2. Now, which library, you have to ask yourself, did that information just go into? The answer is the project library. So if we did something to access the local library, it would go back to the defaults. And the way we access the local library is I'm going to click here on the model number and re-import the local library, and I did that, and it went back to 8.1 and 43.9. Okay? Now, let's say we wanted to go to 7.9 and 44.2. Is that what it was? I think it was. Let's say we wanted to make that permanent and not only affect the project library but the local library. See this button up here that says edit? We go up there and we have the 7.9 and then we have the 44.2. And notice we have a whole bunch of other information out here. This says, up here it says minimum required data dash STC, which stands for standard test conditions. PV Rocket requires an answer to every one of the pieces of information in this. And this stuff out here, it can accept information and it'll store it. It just doesn't do anything with it at this point. We've started storing things that we're working toward using in the future, if that makes sense. So we could make changes here also, like 7.5 on the IMP, and we could hit save to library. Well, first of all, there's save to project, and that's the default. If I pressed enter right now, it would save it to the project library. And then there's a save to library button that will save it to the local library. The default library never gets touched. It's hard-coded. You saw that. Machine code can't get into that again. So I'm going to go ahead and hit save to library. And we picked up the 7.5, we got the 7.9. I'm going to go up here and click on the model number again, and notice that nothing happens because it not only got saved to the project library, but it got saved to the local library as well. Okay? I hope that's clear. Let's see. Then there's the cut. If you want to remove a model from the local library, you would hit cut from library, and it would save all of the data so that you could maybe what you're doing is correcting a misspelling on the model number or something. So you highlight the model number on the previous tab, come to here, say cut, and then go back to the other one and come back and add in the correctly spelled model number, and then hit paste data, and it brings the data back. And I think that pretty much covers that topic. Let's go to add. So there's two ways to add a model. If the manufacturer's already there, you should pull it down and select it. If you're adding a manufacturer also, type it in there while add manufacturer is selected under manufacturer. So I'm going to add Bob's Awesome, which is my favorite manufacturer. And the model number is, I don't know, these are the things that are on my head right now. Short circuit current of, let's say, 7, VOC of 44. IMP of 6.2, VMP of 38.6. I'm making this stuff up right off the fly. 315 watts, coefficient of negative 0.325. That's kind of high. Percent. Don't need to fill the rest of this out. I'm going to hit save. And all I did was add, so if I wanted to select it, I'd have to come back down here and do that. Now, if I want to add another model, the best thing to do is to pull that down, not type it in, add in another one. Cats, come up with different, make different stuff up here on the fly. I don't know why I give so much thought to fictitious numbers. Well, you know, in some respect, I want them to be halfway realistic. Sorry about that. I think probably got recorded. And hit save to that. So now I got two models, puppy and cats. And that's about all I could. Oh, okay. Let's go back to Canadian Solar. And I wanted to go to the one that we had before. And I don't even remember what that was now. It's not this one. Terrific. I don't remember. Doesn't matter. Let's go 938 on that. And 7 on that. Nice round numbers so that we can remember what we're doing. Let's go to Edit and hit Save to Library so that those are permanent. I can click away and I can come back and I've still got the 9, 38, and 7. So that's a CS6K320p. If I go back, and remember, after you've created your local library, you uncheck that default library, and that's the only thing you got access to is your local library. To restore the original defaults, you can come up here to the Canadian Solar, which is right there, CS6K320p. CS6K right there. I got the original data, but I don't think it's saved into the let's just check it. I was trying to figure out if it's saved into the... It did. So going down to the default library and picking Canadian Solar down here and then picking the model, it immediately re-imported the default library values and overwrote your local library. So if you have somebody that forgets and he's supposed to go up here to the Canadian Solar and he keeps coming down here into this and picking this one, then you definitely want him to uncheck that include default libraries and only have access to the local library. And I think that's about all I wanted to tell you about this. I think that covers it on this box. So you can see there was a lot more going on there. You can add your own manufacturers. You can edit. Before the default libraries, every new user had to add and create their own libraries. And so we added the default libraries as just kind of an ad service kind of a thing. And you know, one of the reasons that it turned out to be good that we have a default and a project and a local all separate is, like on the inverter side, a coming thing is the rated current is changing from one project to the next. Even though the cut sheet is the same, they'll both be Selectria PVI 60 TLs, but you'll have, well, that's funny, that's the one that I've got right here, Selectria PVI 60 TL. One will have the rated current at 72.3 and the next one will have 75.6 or something. Why? Why is that coming? Even though they're the same cut sheet and the same model? Because utilities and regulatory agencies are starting to require power factor handling capability inside our inverters. Historically, it's always been one power factor of unity, and now they're requiring other power factors. And as those power factors change, I advocate them leaving the rated current the same. The maximum rated current should be the maximum rated current. It shouldn't be able to change. That's just my own opinion. Derate the wattage is what I would say. So on this, so instead of the rated current changing, the wattage should change. But, and that just makes intuitive sense to me, but the rated current is seems to be what they're headed toward. I just saw something that I should mention. On the inverter side, there's MPPT tracker, so that's maximum power point tracker, and then slash strings. And then over here it says X, Y, Z, no spaces. So what we're trying to convey there, it says 5, 5, 5. So what does that mean? There's 3 trackers. That's why there's 3 numbers. And then each tracker has 5 input strings for a total of 15 on this inverter. And that's the way this is done. Let me check uses DC to DC converter here and have you look at the power optimizer. And we don't have any local libraries, so I'm going to go up and click that again. And we only have one Solar Edge, and it works the same as the others. So I'm going to uncheck that and make that box go away. Now I think I've exhausted everything I can say about my friend box here, the equipment selection. So one other thing just occurred to me. So I showed you the local library, and here's an example, not the local library, I'm sorry, the project library. So here's an example of one. And I just went into one of our projects and grabbed out a local, a project specific library. So we must have done a job with this, an actual job with this China Synergy module and 375 with this information. Now I was clicking around and I created our local library and did not pick this China Synergy. So what happens when you go into a job, you're working with a team, and you go into somebody's project and they have a model and a manufacturer that you don't have in your library on your C drive. And you can see here what it did was it added it and alphabetized it and everything for us. I didn't even know it would alphabetize it for us. But it added it into our local library with only the one model that that job was done with. It doesn't go down into the default library, even though I have that checked. It doesn't go in and pull in the whole library. It just pulled the project library into your local library. And since the project library is only one model at a time, or two if you do 2 modules on one job, but it only pulls in the models that are there, if that makes sense. Okay, let's talk about connection information now. Most of this box is self-explanatory, but there's two things I want to cover. This down here at the bottom where it says conductor sizes, DC conductor size, that's obvious. I pulled it down during the other videos down to a number 10, and that's what it'll use. Minimum ground size is fairly obvious. The maximum conductor size and the maximum aluminum size. You would think that would be obvious, but there's more to it than meets the eye. But I'm not going to cover it in this section of the video. I'm going to wait until we get to this box, the voltage drop box. That's where that becomes important. So the next thing I want to talk about in that box is down here, the service voltage. So we picked 480, we had inverters that were 480, and we had a service that was 480. Let's do a medium voltage 4160 and push enter, and then this stuff became available to us. You need to vet this stuff very carefully because I'm not actually a medium voltage kind of engineer. So I do the best I can, but you should really know what you're doing on this and check it. But it becomes not grayed out. I'm going to go aluminum, MV105, MV90 and MV105. Those are together, mutually exclusive together as one. And then the 100% and the 133% insulation rating is another thing. So right there I've defined the conductors going into the main service from the array. So I'm going to hit next and go through these, and to here, final connection. Actually, let me go through to the end. That'll be worth looking at. So aggregation panel output CB03 trenched. It says output circuit trenched to MSB. It says 2 sets of number 500 aluminum. Down here it says 2 sets of number 500 aluminum and a number 3/0 aluminum neutral and 3/0 aluminum ground. So where is the medium voltage circuit? Let's go ahead and print the feeder schedule even. I'm going to do move last so that I pull out, I'm sure to pull out the last thing, and you'll find there's no medium voltage on here. So what happened? What went wrong? Let's go into final connections, which is 3 boxes after the box that we're talking about. So I click on that. You need to add a transformer in here, or else you can't go from 480 volt inverters to medium voltage service. So let's add a transformer. I click on that. I see, oops, I forgot to hit the NEMA 3R. I hit transformer. I'm going to go ahead and move that up in the lineup. And then I go next. And I'm going to print the feeder schedule and hit close. Move that up. Now we have medium voltage. The voltage output, so it says CB03 to transformer is the 2 sets of 500s with a 3/0 aluminum and 3/0 aluminum ground. And then transformer to disconnect and disconnect to main switchboard are all medium voltage. It says 4160 3-phase. It goes from almost 500 amps to 57 amps at 4160. And it's got all the aluminum 105, 133% that we talked about, and all that's laid out for you. The voltage drop goes to, I almost said obsolete. Well, kind of. I guess that's kind of correct. I don't want to use the word negligible either. Just not relevant, because if you if it dropped, which it's not because it's only 57 amps, but if it did drop, there's taps on the transformer that you could change, I believe. Now, I already gave the disclaimer that I'm a low voltage kind of guy. So it's not, doesn't enter into the voltage drop calculations. Boy, I got some voltage drop that's actually pretty high here. I guess we'll cover that when we get to the voltage drop box. And then as far as the conduit and the fill and everything, we assume that these are kind of direct burial kind of cables is what we assume. Most of our customers do it that way. And it's delta connected to the service, so there's no neutral, and the bonding conductor is a part of the medium voltage cable as far as I'm aware. I might sound kind of iffy on this, but I believe that's how it works. This is how we show it, and it works out every time. Let's go. Okay, so that's not obvious. So let's go back in and look at the next thing that's not very obvious in the connection information. So here we're telling it that the combiner box to inverter. What are we talking about? Strings per box. This is where we define as a system how the strings get into the inverter. It may seem like a strange place to put it, but this is where it's defined. So right now we're saying that the strings go straight into the inverter. If you want to go into a combiner box, a DC combiner box, first, I'm going to hit next and show you a little warning box that pops up. It says, if using a DC combiner box, a number of strings must be specified. So how many strings will the box accept into it? Let's say 3. And I'm giving it a number specifically for a purpose to show you something. Yeah, let's do that. And so that's where that's defined. So I hit next. And there's almost no changes here anywhere. Let's say DC Calcs. Actually, I'm going to close because, let's see, our insertion points are frozen, right? I believe they are. Let's just get all of this out of the way so that we don't get confused over what just got printed. So I'm going to go up to the results box. And say DC Calcs and hit close. And this is what comes in. There's a little bit of overlap there. That's what I was looking for. So this is the DC string amperage area. And let's see. So sometimes it helps to have little divider lines in here as you're learning this stuff to see where one set of definitions begins and the next one starts. So this is for one string going in. It's a 2 number 10s, and that's it. So if you look at the one line diagram that I pulled down here, basically this is 2 number 10s. And actually we need to reprint the one line diagram, I just realized. So let's do that too. So I'm going to go to the end and hit print one line. Now it looks like nothing really changed there. I'm going to move this off to the side, and to help reinforce it to you, I'm going to make it look a little bit better by pulling the dynamic block around. There's a block here that you're not seeing that wasn't printed the first time. And it is a string box. If you go into the options, you see that the DC abbreviation, so the DC name is combiner box, and this is all customizable. And then the string box is SB for string box. So a string box got printed that wasn't printed before. So, you know, you pull this stuff up and make it look right. Let's make it a little bit taller. Sorry, let's make it a lot taller. So this is kind of what it prints. Now, like I said, PV Rocket, we've kind of backburnered all that stretching that I just did there. We'll get to it, but for now it's all done manually. So what did we do here? What is the string box? We told it that there was 3 inputs per output. So really what we are going to have is 4 tracker, and each one has a maximum of 3 inputs. Like that. This is what we told it. I'm not saying it makes sense. PV Rocket will let you do it. You really have to know what you're doing and what your input and outputs are. Because we got a problem here. We got 4, and you could copy this and make it 2. You could do whatever you wanted here. But just taking it at face value that this is a DC string combiner that has 4 different separated sets of inputs that each receive 3 strings. Well, we only have 3 trackers in our inverter, so we probably wouldn't want to use all of these, but we would have to because we got 12 strings. So we would use the separate DC array, or separate DC array, the same way that I showed you on the other video. So what I'm doing is running the program, clicking on the strings that I want to put, and then I click on the circle over here to get them out. And actually it just occurred to me I don't even need to do that because we're using every string. We're using every string here. So I could just go to insert and find, insert the array lines, and close. Like that. And then over here, And I picked this for a reason. I picked 3 because I want to show you there's a big difference coming up later. So over here we want to adjust it, the inverter, and there's a couple different ways of doing it. You could take the inputs down to only 1, and then move these around like this. There's that way. And we're 1 short. We could change this. So these are lookup tables that affect how many fuses there are. This is a lookup table that affect how many trackers there are. So if I add that one, we could do it that way, like that. Just like that. Now there's an alternative, by the way. Let's see if I can get this right. Yeah. So I changed that to 0. And then this one over here, I come up with up to 33 of these things that you could have going directly into the inverter. Otherwise, you would think that the limit was 8, and it's not. It's not. Let's see what 0, 0 does. 0, 0 took the fuses away. There's all kinds. 0, 8 also took the fuses away, but gave us the ability to have multiple inputs. See, there's this thing has a lot of options here, but let's go back to the way we had it, which was like this. Like that. So what we do is, this says to number 10, so we put text up here that says to number 10 something like that, but we replaced the arrowhead with a loop. So the next thing we do is, here's a calculation based on 2 strings in parallel, and I actually wonder why we got that, because I'll have to look into that. I don't see anywhere where we have 2 strings in parallel. Oh, I get it. This one that has 15, you don't want to put with the 18s, and so there will be, this is where we get, oh, and also, let's see, 3, 6, this is where we get 2 strings in parallel, so from that one. But here's a calculation that shows we have 31.2 amps when we have 2 strings in parallel. When we have 3 strings in parallel is down here, and we get 46.8 amps on a number 8. And so there you get a size, and I'm not doing this in a pretty way. Maybe another video I'll have our actual way that we do this in here. But there's where you get, and that's how you do it. So I've told you in another video that these tags over here relate to the feeder schedule, and the DC side is not scheduled, and you do it like this. And it's all calculated for you, but you have to go look for it and find it. And that's the basics of what I wanted to show you right there. Now there's more to it. Let's look at the array that we did. Inverter 1, here's the strings. So let's see, did I print the, I don't think I did. I just got the DC calcs. So let's go back into the calculations and print the DC voltage drop. DC voltage drop table, and I hit close. And that came in right there. Now, let's look at inverter 1 string 6. It says 18 modules is the quantity. It goes 92 feet. It's got 9.6 amps on it. It's number 10 gauge wire. The resistance per 1,000 feet for number 10 gauge copper is 1.24. The maximum power point voltage is 7.02. The voltage drops is 2.19, which is a percentage of 0.3. Notice the distance of 92. You might say, what you'll do is you'll look at that and say, well, it's measuring from this end to that end, and then from this end to the inverter 1 is 96 feet. Let's check that. It's true, but let's check it. Actually, that's probably supposed to be at right angles. Let's check it anyway. Yeah, that's 62 feet so far. So how did we get it? So let's measure it again. So I draw a polyline over the top, and then I draw it right angles out like this and come up, and I get 65 feet. So in the options tab, there's this option right here. It says include string length in DC voltage drop table. So if I unchecked that, then it would just be this little segment over here. So it depends on your understanding of voltage drop. I have some customers that tell me, of course you can't include that. And then the other ones say, well, of course you have to include that. And I stopped caring a long time ago on it. Let your customers tell you is what they want, is what I say to it. I think the actually correct way of doing it is unchecked without. That's my own personal opinion that I've come to believe, but you're never going to convince your customer of that if they tell you to include it, is my opinion. And I'm trying to remember if the right angle or straight line is picked separately from the AC or not. But anyway, the next thing you should be saying to me right now is, well, what happens if you've got string 12, 11, and 10 combined to a DC panel up here, and then run that, what did we say it was, 65 amps? .8 amps, and then run that 46.8 amps down here to the inverter. How do you do that? I mean, look at that voltage drop table. It's not even on there, the combiner panel, the DC combiner panel. So how do you do that? How do you get that to go in there? Well, let's take one of these. Oops, I erased it. I was supposed to copy it. Let's take one of these up here and call it SB01. Now I called it SB because that's the abbreviation for DC string box, and I called it 01 because it goes to inverter 01. So let's just start at the first box. and go through one by one and see if we see anything different. We do. Oh, look at that. Here's an opportunity to tell a box you've never seen before. It's a chance to tell PV Rocket which strings go to which string box. DC combiner box. It's titled DC combiner boxes. So if we know, let's do it, let's just mark it. 1 through 3 go to box A. 4, 5, and 6 go to box B. I'm clicking the first one and then holding down the shift key and clicking the second one. 7, 8, and strings 7, 8, and 9 go to box C. And string 1 through 10, 11, and 12 go to box D. So now I press enter and go through the boxes. The boxes aren't changed. And then I press the DC voltage drop table. Now let's go look at the box. So string box 1A has 3 strings on it. Goes, the 23 feet must be from box 1 to the inverter. And it's got 28.8 amps, which is the summation of its 3 strings. It needs a number 8 wire. And there you go. And then string 1, 2, and 3 have distances like this. 5 and 6 were the ones that were closest. And you see that it has the lowest distance, but it's still kind of long because we still have the include string length checked in the options, right? So that's how that works. And it goes down to box D and so forth. Okay, so all this box 1A, 1B, 1C, and 1D are all 23 feet from the inverter because they're all 23 feet away because they're in string box 1. Okay, so the next thing, so that must be 23 feet right there. So the next thing you should be saying to me is, okay, but we don't always do that. We rarely do that. Sometimes we do it, but sometimes we don't. Let's look at inverter 2. And I wanted to change it first. So let's do a string box 2, and then let's help it with the definition using the same format that it just used with us. A lowercase a, b, c, or d. Like that. Oops. And now let's rerun it. And let's start from the beginning so that we can catch the string box 2. So there's string box 1. Now notice something here I'm about to show you. It's got 4 possible outputs from the string box because we said 3 strings per box. I press enter and move to the next box and we only have 3. When you enter it, it'll be blank like that. I had data in there because I'm recording these videos out of order and I was doing something else. So when you enter it, it'll be blank. But notice we only have 3. Why? It's got the same information that 1 did, but now we have 3. The reason is that when you take the extra step of putting in the lowercase string box identifier and break it up, it no longer does that math of dividing the number of strings, 12, by the number of strings available in the string box, which would be 3, and the dividing factor is 4. It no longer looks at that. That's not what it looks at anymore. So what does it look at? It looks at the number of trackers in your inverter. Now, I'll just pause here and say that PV Rocket's been under development for 5 years. And the reason we have these 3 different ways of doing it is by request as it was being used by the beta testers. So first level, it's under development. We've got hundreds of lines of code to write. I'm not making excuses or anything. In fact, I'll just stop at that point. But as it's been developed, we've approached it from different ways. And so we have these three different ways. You can just go SBO2 and stop, or you can add the subscript and break it up, and you get only the number that corresponds to the MPPT trackers in the inverter. So I put a SBO2D out here, but I don't need it. It's not going to be read, and it doesn't affect anything. So let's do string 1 through 4 on A, 5 through, let's mix it up so that we can see it. 5 through 9 on B, and 10 through 12 on C. And go next. And then let's look at that output. So I'm going to push the string DC voltage drop table and close. Oops, and I got two tables on top of each other here. Erase both of them, remove the last. There. So we still got string box A, B, C, and D, and then we got string box 2, A, B, and C, and we got 4 strings on A, 5 strings on B, and 3 strings on C, just like we told it to do. The amperage, is that the amperage column? Yeah. The amperage column adjusts appropriately. The distances all change. 9 feet for A, B is 7 feet away, and C is 28 feet away. Yeah, A and B went on either side of the inverter, like that. And notice if you don't put anything in, then it behaves like it did before, and it's just measuring the distance to each inverter, if that makes sense. So you can kind of play with it and adjust it as you need to. So this is the connection information box video, and that whole DC thing is probably the least obvious thing that PV Rocket does. Everything else you can kind of figure out by clicking around and everything, but we have to admit the DC string box combiners probably not going to figure any of that out. So if you have suggestions on how to make that more intuitive or anything, we just kind of figure you're going to have to rewatch this video as jobs come up that have remote string boxes, unless you're doing those daily. Anyway, yeah. So we covered the medium voltage connection down here. We covered that, and like I said, we're going to cover there's a lot going on with the maximum copper size and maximum aluminum size, and that also is not obvious, but you could at least everything is there in front of you. You could figure it out if you clicked around and played around with it enough. But we'll cover those on the voltage drop table. So that's what we got for this. Thanks for your time. Now on the voltage drop box, there's a few things going on here. So on the top here, we have a cost report, and I've shown you this before in earlier videos. You got almost $5,000 in estimated cost of the 3 aggregation panels here in our fictitious project, and then you've got the DC cost that popped in there after we strung it, and then we got the total cost that includes these feeders down here. There's also this trenching over here. Let me close and show the trench path real quick, because it doesn't take very long. So up here on the support functions, there's one called trench path, and you click on that, and basically where you envision trenches to run, that's where you put it. and one over here to the main switchboard. So that's not really intended to be shown on the drawings like that or anything. It's just for the estimation purposes. So if I go back into the trench voltage drop box, now it's populated with trenching. And you can save a cost report, and let's do that. Let me figure out where this is saving. Documents, PV Calc. And there's one there that's saved already, and that one is produced. You can't stop that one from being produced. That one's always produced, and it's stored in your library path. And let's do saved cost report 2020 and hit save. So that saved a cost report, and I'll show you that later. Actually, let me show that to you now. So this is the cost report that we just did. It's saved under saved cost report 2020. It starts with PV installation cost material. It's just the material and not any labor or anything like that. That's going to be a future copy of PV Rocket. Custom prepared for job number, and then if you have a path, anyway, that's customizable. And produced on 5/30/20 when I'm recording this video. So we have combiner cost 1. And this is the output of the run. This is the output of combiner box 1. It's 3-phase, 700 aluminum. It gives you the cost per foot. It says approximate ground conductor because not all the calculations are finished at this point. So it could be changed in the final QC control at the end. Probably not, but it's possible. 1 AUG aluminum at 32 cents per foot. Neutral, again, 1. Got the conduit size, PVC. Number of parallel runs, 1. Distance of this segment, output segment. And then here's the equation that it uses to get the cost. And then there's the cost of the run, $1,374.29. And it comes down here for each of its inverters that's connected to combiner 1, and then it goes to combiner 2, and it does the same calculation, and then same for the inverters. And then you get down to the end, and it's got a DC cost. We had 623 feet, a cost of $1,500 at 20 cents per foot. Trenching cost, 1,200 feet is $8,500 at $7 a foot. Aggregation panels are $1,500 for the 400 amp and $1,700 for the 600 amps, and then the total cost is $15,000. All of this is customizable. So here is a file called values. And values is a very powerful file. And it's stored, let me hit close on that and show you where it's stored. So if you hit options, it's stored with the library path. If you look at C support PV Rocket values.txt, that's where it is. So values.txt, here's it's kind of readable, and there's comments after the semicolon there to help you understand a little bit about what's going on. So up here is wire conduit. It says, copper wire. And then if you read this, it should make sense to you. Let's take this one for example. Number 1, 75.130. And you can kind of guess, and even up here it says 75 equals 75 degree column, 75 degrees Celsius column. So the 75 degrees Celsius column for number 1 is 130 amps. The 90 degree column for derating is 145 amps. Circular mills is what that one is. The DC resistance per foot. The impedance in EMT for a power factor of 0.85 is, I shouldn't have done that, got to keep it highlighted, is 0.16. The complex impedance in PVC for power factor of 0.85 is also 0.16. AC resistance in EMT is 0.16. AC resistance in PVC is 0.15. The square inches is the, I'm not sure what that's used for. If we have circular mills over here, that's probably for conduit fill. And then right there is a dollar sign. $1.37 and 57 thousandths of a cent, or hundredths, or whatever. And it's all right in here, laid out. And that's the way you do it. And here is, oh wait. There's PVC, and there's its cost, all laid out. Here's equipment budgets. 600 amp panel is 1,665 for 208 or 2,100 for 480. Is that what we just saw? Here's the miscellaneous cost down here. PVC wire, PV wire is 20 cents and trenching cost is $7. And it's all laid out here for you to customize. One thing I want to point out while I'm in here, I get this all the time, is these fuses value. Look at these fuses values. This is straight out of the NEC article 2. No. Anyway, it's not jumping out at me. There's an article that lists standard overcurrent protective devices. There it is. Oh, I was on the right place. 240.6A. So this list comes straight out of there, and that's what you'll get when you download it. Well, what if you want to... They do make other fuses than this. So one that I get all the time is 900. Well, somebody will do an array that produces 825 amps, and PV Rocket will put it on a 1,000 amp breaker and design accordingly. And we'll get that email and say, this is unusable, I can't use this, what happened to 900? Okay, well, if you can't use it, there's nothing we can do about that. But if you wanted to use it, there's how you do it. Done. Now you got a 900 amp fuse, and PV Rocket will adjust all of its answers accordingly, just based on what I just did right there. You got to do it in order. You can't put 900 at the start. And that's what makes values.txt such a valuable and important file for customization. You can go through here and adjust things and get a different answer than you did just a second before with the same software. And that's how you customize it. So here's your cost report. So let's go back to what we were doing, the voltage drop box. And that's the cost report up here. So based on an impedance with power factor, so all this voltage drop, if you change the power factor down to 0.85, you could see this stuff adjust real time. Like this inverter 5 is showing 1.7% voltage drop. If you change it to 1, it goes down to 1.2% voltage drop. Power factor is something that's coming in our industry in the United States. It's in other parts of the world already, and it's starting to be a concern, and it's on its way, and PV Rocket is ready to help you with that. Now, I want to talk about parallel feeders, and to do that, I've kind of prepared for copper, and these main feeders are aluminum. So let's go back and redo our calcs at copper. So I'm going to click copper right there and copy first to all and take copper through. And now I've got a copper system. And let's go to the end and print a new feeder schedule. So I think it printed it right over the top of an old one. So I did move last. And I have copper everywhere, even through the feeders. So look at this 289.2 amps output for combiner 1 to combiner 2. And it says it put it on one run of 500 copper. So one run of 500 copper out of the 75-degree column is 380 amps. So 289.2 amps. Why so high? So that 289.2 is for voltage drop calculation purposes. It's the maximum amperage anticipated for what we're doing out of combiner 1, but it's not what we base the circuit or fuse on, because it's a continuous load, so we have to add 25% to it. So 289.2 times 1.25 is 361.5 amps, and you can see from the chart, number 500 copper, 380 amps, so that's correct. And you can go through here all day. We encourage you to. This is all correct in what we're doing. So let's go back to that voltage drop. And I want to show you something about how it works. So I told you on the quick start video that this up and down is conductor size. It's not 100% accurate to say that, but it's close. Let's go up on this main feeder and watch. Inverter 4 is at 4.5% voltage drop. As I go up to 600, it dropped to 4.4. Now it's down to 4.3. Now it's down to, it's 4.3 again. And I can go up over here on this one, and it also will affect it didn't do it. It is doing it, but it's just not getting the percent to change. So I'm going to hit up one more time on this 750. And it went to two parallel 250s. Now why? Why 250? So two 250s is good for 250 kcm is good for 255 amps times 2 is 510 amps. Now I thought we just agreed that we were trying to cover 289.2 times 1.25 is 361. So 361 divided by 2 runs is 180.75. Why didn't it go down to 3/0? Seems like 3/0 would have been the minimum on that, but we got 250. So is it really correct to say that it's increasing the conductor size when you go up? Not really. We're going from 750, we dropped to 250. We think we should have dropped to 3/0. So what does the up mean? Up is the ampacity increase. So we went from one run of 750 up to, which 750 is good for 475. So divided by that, that's 237.5 amps. The next size up is 250 kcm, and that's what we got. So I drew out a little chart here for you. Let me hit close on that. So down here in this chart that I drew, we got all copper, 1 parallel run, 2 parallel runs, and 3 parallel runs. So if we're going to go up in ampacity on 475, we need to find something over here that's greater than 475, which is 250 kcm. And then you run parallel up to 950, and you got to find something over here that's greater than 950. So that would be number 400 kcm. And that's why we went from 750 to 2 parallel runs of 250. We looked at and agreed that we're trying to cover 361 amps, and we could have gone down to 3/0. But that's not what happened. So that's what up means, is up in ampacity. So the next thing you should be asking is, well, what if I wanted to do 2 runs of 300? Why can't I do that? Well, you can. There's 2 ways of doing it. First, if you want to do 3/0, you could look at that run of 400 and say, if I cut up here at a maximum conductor size of 500, that would get me the ability to have a 3/0. And let's check that. So I'm going to enter into the connection information. And down here is maximum conductor sizes. And I'm going to set it at 500 kcm. And go to the voltage drop box. And it's already at 500 kcm because that's the biggest size that covers the 361 amps of output. .400 is good for 335, so we just barely made it. So if I go up on this, I get the 2 runs of 3/0 that we asked for. Okay? Now, let's say you got 2 runs that are the same. And one of them you want 2 runs of, you want to make it parallel 2 runs of 3/0 because it goes a long distance and you don't want to pull that great, I don't know, whatever. You want 2 runs of 3/0. And I just showed you how to get it. But what if on the other one you wanted to do a run of 600, 700, or 750? And I just told you that to get the 3/0 on one run, you had to do a maximum conductor size of 500. So now what do? So let's go back into connection information, and this is the second way of getting what you want there. Instead of pulling this down to 500, there's a setting up here called flexible. And you could make that your selection. And we're at 1 run of 500. We already decided that's the smallest wire size for 1 run. And we can go up, and it allows us to go up to the 600, 700, and 750 that we wanted. And then when we go to parallel, we're allowed to go down to 3/0. And so that flexible setting takes away this whole thing. So inside PV Rocket, there's a subroutine that sizes every wire in the system. And the name of the subroutine, and the only reason I bring this up is to paint a mental picture for you. The name of the subroutine is ladder. And it's always climbing in ampacity. 750 goes down to 250, not 3/0. and so on and so forth up. But one way of overcoming the latter and doing what you want to do is to set a maximum conductor size. And that was how we did it originally. We got a lot of people that said, coincidentally, I drew a line here at 500, and that's where the line in the sand has been drawn by a lot of our customers. Is they don't want to pull, they don't want their electricians to pull 750 copper. If you've ever tried that or seen somebody try it, that is not fun at all. That is a lot of work. I come from an industrial environment, and they do it all day, and they take great pride in being able to do it, and seeing other crews that, oh, that's hard work, I'm not going to do that, give me a maximum conductor size of 500, I'd rather do more parallels. But the industrial guys are, no, they consider it a personal challenge, an insult if you say they shouldn't pull 750. But this whole time I've been in solar, oh, let's make it easier on the guys and put a smaller wire in. And so that's where the maximum wire size came from. And then here recently it got pointed out to me that somebody wanted a 750 run on one for one reason, and then another run that had the same ampacity but did a different circumstances. They wanted the 3-aught put in, and there was no way in PV Rocket to do that. So we introduced the flexible setting there. So I think I've covered all I wanted to cover on this voltage drop box. Let me go back to it. I should have pushed the voltage drop, and I didn't. We covered the cost estimating. We covered that. There's also the quick start video that you could watch, but I think we did this box for this video. Thanks for your time. Next thing I want to talk about, invariably as you finish the project, you have a site plan and a stringing plan. And I've seen it done a million times, and it's fine. You could do this. But people take their design, they copy it from one drawing to the next, and then they make up their construction documents, they hit print, they send, everybody's happy. They're thrilled, everybody's happy. Then plan check comes around, or the owner makes a change, the module's no longer available, whatever's going to happen, they come back and they call and make a change. You come back in and you rerun PV Rocket, and you run it, and you continue on, and you get this error message, which says that it's turning off the voltage drop required to off because it can't measure anything. The first time I showed you this box, it was because we didn't have blocks in there. Now it's saying there's multiple blocks. And I've gotten those emails more times than I can even count. No, I don't have more than one block. It's messed up. So I created this insert and find tool. So far we've only looked at the insert. And you could click multiple things at once. And here's the insertion points that you can click on and insert without having to run through the program at all, and help you create your template. But there's also this find command, and I actually like this a lot now that I've done it. It gives you the ability to go through here and see that you do have more than one of something. Let's see if I can find a good glaring example. Here's a main switchboard. Did I only make one of those? Anyway, let's look at how this works. So there's inverter 4 string 5. So you could hit view on that. And there it takes you to inverter 4 string 5 on the first one. Go back to it. And here's an inverter 4 string 5 from the other one. You hit view on that, and it takes you to the one. Oh, it took me to the first one. Okay, well anyway, you get the idea. Same thing happens with output points. You put the output points into the drawing and then freeze them, and then you don't know where they are anymore. And so you could select on it and hit view. It'll take you to the model to the tab and show it to you. And you can also, if you just can't find it and it's showing you two of the same thing on all these, you could just hit erase. Just forget about it. Erase them. And that'll help you clear things out. So just a little bit there about insert and find. So we've done a complete fictitious job here that had 7 inverters, and we talked briefly about creating your construction documents and getting them out. Let's move on to another topic about multiple points of interconnection. For multiple points of interconnection, on the PV Rocket ribbon, you can see where it says only one POI, point of interconnection. If you go to the add-ins tab, it's here on the top, only one point of interconnection. If you have multiple points of interconnection where you're connecting to the utility service 2 or more times on one set of drawings, it's really advantageous to use multiple points of interconnection. So instead of only one POI, for the first one you would pull down point of interconnection number 1 and go about your design based on that. Now let me do a string system here real quick, as fast as I can, because you've already seen all this. And I'm not even going to talk very much. I'm going to point out the nuance differences as I go. So I'm going to go to insert and find, insert a module and a inverter block. Hit insert. Put the the module in there. Put the inverter in there. It goes back to that. You hit close. Now right here is the first difference. In the what I showed you earlier, you would type in inverter 1. But here we have to put in a leading 1 for system 1, inverter 1. And I'm going to put that there. This one's going to be inverter 2, 3, whoops, 4 and 5. I'm going to use one combiner box. Let's see, what am I calling the combiner boxes? CB, I think. And I'm going to put my main switchboard right next to each other because I'm going to say that they are the same switchboard. One MSB. I'm going to string it first this time instead of running Calcs first. So I need to know how many modules we have. 360. and I've got 5, 1800. Great. So I run stringing 1800, 360, what did I do? Did I do that backwards? Oh, 360 per inverter, not 360 inverters. 5 inverters. Better. But it already guessed 5. So just put 360 in there and copy first to all. I've already talked about this. Notice as I'm going through here that there's a POI number 1 listed up there. That's to help draw a visual reminder of what you're doing and which one you're working on. Just in case you think you're working on POI 2 and it's actually set to POI 3. Just a little visual reminder as you're working along. So I'm going to color code. Whoops. I think I said there was 18. Yeah. I like speedy select more than speedy strings. Now notice as it drops the labels in, it's saying system 1 inverter 5 string, and it says SYS 1 to be precise. That is customizable through the options box. It doesn't have to be that long of a sentence of data there. Now I'm going to do a speedy copy and tell it inverter 5. And it's copying that inverter to the others. And it takes it a little bit. If you're doing a megawatt, you actually have time to go get a cup of coffee. And now it's strung. So now I can run the calcs. And it's blank. But you know we've selected things because we already did the fictitious job for only one POI. But this is now for POI 1, and it keeps track of everything separately. So I've never used that before. I just picked that stuff at random. Let's go to that one. I need to stay in stuff I know have vetted a little bit. Let's do an SMA. That only has two trackers and one string each. So let's do something. Let's just stay with the Yaskawa Selectria. Now, when you saw me do the other one, it asked me how many inverters, but this time it didn't. Why? Because we already strung it, so it knows how many inverters. Doesn't know a whole bunch about what's going on, but it does know how many inverters. So I define a bunch of stuff there, hit copy first all, and move on. Now, no matter what, even though I've got the box already in the drawing, it doesn't, there's no way for it to know how many aggregation panels we have. So I'm going to hit aggregation panel 1. I'm going to combine all 5 into one. Trenched output, let's make it aluminum. Let's go ahead and accept that, that's fine. Oh, so my string voltage exceeds 1,000 volts. It'll let you keep doing it. There are 1,500 volts, and there's a way of making this one accept without that warning box. Anyway, I'm just trying to get to the end because you've already seen all this. So fault currents, I'm going to go ahead and say this, and I think we talked about this on another project. And normally you have a template where all this is, and you might be saying, well, you already dropped all these in before. Yeah, but that was for a different POI. So every time you have a different POI, you got to drop these insertion points in again. There. That's a whole bunch of calculations done very quickly. And remember to stretch this stuff out. And you could see all this on the quick start video. Oh, here's something to point out. I'm glad I zoomed in on here. So you stretch out the array and see how much space it's taking. It's right up to the end, and there's information in here. Sometimes it gets even longer than this. And look at this little pull arrow out here on the left. People forget that it's there, and that's what that's for, is when you get really long stuff. Let me see, is there anything else to show you? I don't think so. So that's how, what I wanted to show you there was how you get multiple points of interconnection done. And now you can pull down a POI 2 and move on to your next one, which we'll do in the very next video, and we'll do the next video with microinverters. So you get exposed to multiple points of interconnection and a microinverter at the same time. Thanks. So let's talk about microinverters now. Let's in the previous video we did point of interconnection number 2, or wait, we did number 1, we were about to do number 2. Yeah, I think we were about to do number 2. So let's borrow one of these blocks and reset the color code on it, always using the support function. Don't do it yourself. Create an array of that block. Now, I don't know that I've ever personally done a microinverter project, but I don't know if 26 microinverters long is a long string circuit or a short one. but usually they're smaller projects. Explode that array so they're individual. Let's borrow that combiner and turn it into system 2 CB01. If it was only one CB point of interconnection, now see that we know we're on system 2. We switched from add-ins, which is set to POI2, to PV Rocket, and that one still says only one POI. If we the developers can figure out how to uniformly change those, we will. You're probably not going to be switching back and forth from one to the other like I am, so it shouldn't really be a problem for you. And we need another MSB. Put it right over the top if you're saying that you're connecting all into the same board. I don't think PV Rocket allows you to use microinverters and string inverters into one combiner in one point of interconnection. I don't think. I think if you tried that, it would tell you that's an unsupported function. So let's see, can we go straight into Calcs, or do we have to string it first? Usually they're independent of each other. I wonder. I'm going to run the Calcs program. Let's see, in phase. I don't know which one is a good one, the right one. Oh, you know what? There's voltage outputs listed here. Oh, that's interesting. They're all 208 or 240. That makes sense. I'm just going to pick that one. Does that look right? Yeah, that looks right. Sure. Module per microinverter. That's the first time you've seen that pop in. That's showing one. So it's a 1-for-1 system. Sometimes you get two modules onto one microinverter. Sometimes 3, 4, I think is the most. And but this is a 1-for-1. So looks good. I think that looks fine. So we hit next. Always got to fill in your project information. Voltage drop required, 2%. Try to make the number somewhat realistic. Now, here it would be talking about inverters, but now we're talking about microinverter circuits. So I'm going to add 4 circuits. And we get a little bit different behavior. I'm glad I went into the Calcs first instead of stringing it first. So we get just a little bit different behavior here. This is just like on the previous videos for string inverters, this is the description of the AC output of the circuit. So I'm going to say it's roof mounted, copper. Go ahead and derate the neutral. I'm not sure that's relevant. I wonder if there is a neutral. I don't know that much about microinverters. But you can hit none if there's no neutral at all. 2 current carrying conductors. Wait, let me go back. And look at that. 208 volt. Oh, it does say single phase. Okay. Now, that brings up an interesting point, though. We could make it 3-phase because, in fact, let's do that. So let's say that there's 3 current carrying conductors in the conduit and change it to 3-phase. Now, notice how it went from 13.5 amps to 7.79. So in phase, the output is 208 volt single phase out of the microinverter, but as it goes in the circuit, there's a wiring harness made by the manufacturer that can combine those up and put three-phase out of the circuit. And that's why there's still the ability to change right here, separate from the inverter itself. And also notice that on the bottom here, PV Rocket actually took some guesses at what's going on for you. There was a lot of debate during the development of this, and that's what we did. So just slight twist of behavior on a box that you should be very familiar with if you've been using PV Rocket for a while, and this is your inverter output. Let's do copy first to all, and I think I've got it all set now. And if I hit next on this and I'm missing something, there's always a warning box that pops up and tells you missed something. So you don't have to sit there and stare at it for too awfully long. An aggregation panel. So we did do CB01, and this is POI2. So I'm going to combine all four of these circuits into it. The output is trenched. Let's keep it copper. Whoops, I missed one. And I've been making videos for a long time now, and we're stringing them together in one super long video, and then we're going to time index them to be contextual as you use PV Rocket and hit the help button. It'll pull up the right video for you to watch, the right video segment, but it's all going to be one super long video. Don't sit down and watch it and then drive. You'll drive drowsy. Anyway, I distracted myself. I think we're there now on this one. Let's go ahead and say that, yeah, there's a fuse disconnect. That's fine. Oh, we didn't circuit it. So let's run the strings then. So here's the output. If somebody's asking you for a quick one line, yeah, we've covered all that in previous videos. So I'm going to hit close on that and run the strings. Let's see how many. Always got to know how many. 104. So run the stringing program. 104 modules, 104 inverters. Microinverter circuit quantity is 4. Now that was pre-populated because we already ran the Calcs program and told it there was 4. So the two programs run independently, but they also feed just little glimpses of information to each other for harmony's sake, so you can help you out. So modules per each circuit. That was a horrible guess. I think I know why it guessed that. Okay, that's kind of inside the weeds. It's 20, isn't it? I thought I did 20. Apparently not, because I did 20. I did 25 or 26. That's what I did. I don't know what the right circuit length is on a microinverter. I did 26. So, and I know that, if you watch all the videos, not at once, the modules remaining shows me that I'm balanced with what I showed at the beginning, which was 1004 or something like that. Yeah, 104. So I hit next. Now, if this was a string inverter, we'd be on color coding, and then there's a couple other boxes, and we just skipped right over them, right? Color coding doesn't make any sense to us on a microinverter project, because the only reason to color code, well, that's an exaggeration. One of the main reasons to color code is to get you access to speedy strings. Speedy doesn't make sense to us in microinverters because We lose out on the ability to do repetitive tasks in microinverters, and they're smaller projects typically. I'm going to leave it at that. So we don't even allow color coding on a microinverter project. So we skipped over a couple boxes. If you've gotten yourself familiar with PV Rocket, you know that something just got skipped there. So now we're into what, if it was a string inverter, this is the stringing end box, but now it's called circuits. So if you watch the rest of them, you know what's going on here. I'm going to go with sequential because it's fast. I like fast. And it dropped on system 2, circuit 1, system 2, circuit 2, system 2, circuit 3, system 2, circuit 4. So now we can go back to our verify distances on the Calcs program and get to our voltage drop calcs. And typically you're not even going to be worried about this. If you're doing a residential microinverter system, you could, on the second box where it says voltage drop required, minimum 2% or maximum 2%, you could just leave that turned off and you will never even see or get used to this voltage drop or the distance box or anything. But we do have some big voltage drops here. Oop. I don't know why I'm doing this for a fictitious job, but there, we wound up with number 8s on everything and a feeder of 750. Let's take the 750 down. That's looking good to me right there. I'm going to lock that in with a save. Yeah, the 120% rule is it looks to PV Rocket like it's being exceeded. That doesn't surprise me because I put 4 circuits and I think I said the service was 400 amps, so that means I could put 80 amps out, and I probably exceeded that. I was making up numbers, but we try to help you. A little warning: make sure you looked at this, make sure you looked at that. You can do fault currents on a microinverter system. Not sure why you'd want to. I'm gonna go ahead and just get me some outputs for you to look at. We'll put them right here. Yeah, DC voltage drop calculation. Look at that. That box is nice and empty because it's a microinverter circuit, so it's going from right out the module straight into an inverter that's 2 feet or a foot. Not going to happen. So it'll print out for you. That's kind of funny to see when you've been doing the string inverters for a while, because normally there's an inverter here and this is the array, but we don't have inverter, it's microinverters. Equipment schedule. There. So let's see, what are the big differences on this? So it says 26 modules and 26 in-phase microinverters. And on the equipment schedule, there's 2 things in here at a time. So it says 1 and 2. That equipment tag goes to this equipment schedule right here. Number 1 and number 2, module and inverter. So that's the way we show it. I don't think there's any reason to ever stretch that around or play with this stuff like there is on the others. You're gonna move this up in line, and I showed, even if you're doing residential microinverters, I would say that you need to watch the quick start video, and you'd be better advised in fully knowing PV Rocket and watch a lot of this stuff. There, and I'm not going to go through it all again. There's your microinverter outputs. From System 2 Circuit 1 to System 2 Combiner 1, etc. We went all into one. The combiner went from combiner to disconnect to System 2 MSB. And that's how you do it. Let's see, is there anything else I wanted to tell you? I don't think so. The amperage output of the PV is just, it's the same as for one module as it is for a string. The voltage is down to only 51.47 because it's the corrected output of one module. Yeah, I think that was all the differences. Thanks for your time. Now, I almost forgot power optimizers, or DC to DC converter, as the National Electric Code calls them. So if you've been watching these, I've got 3 different systems designed here to 3 different POIs. Let's go back to the first one, which wasn't POI number 1, it was only one POI. So I just switched the system over to only one POI. And let's go back to that one. So I'm going to hit the Calcs on that. And let's change our inverter definition. And instead of Yaskawa, let's pick Solar Edge. And let's go with this 100 for inverter grid tie 1. Let's pull that down and switch the other one to a 66 for grid tie 2. For power optimizer 1, I picked 400. If you were watching all the videos, I picked that a while ago, and it picked up that. Okay. So I think that's it. So not much changes here. In fact, there's also a thing called the rapid shutdown device that's coming up now, popularity, because of the inner, what do you call it, the inner array rapid shutdown requirement inside the array, not just within 10 feet outside the array. So we don't even, PV Rocket at this point doesn't even address those rapid shutdown devices at all, because it doesn't change anything on the calculations. Now, the power optimizer does. It actually does things slightly differently. And you could see here on the inverter, one difference is this little inverter optimizer type right down here. If you had 2 different type of power optimizers, OP1 versus PO1. Wow, 5 years of development. I've never noticed that before. I've seen some strange things in here as I go through and verbalize all this. I'll have to fix that. Should be PO1, Power Optimizer 1, not OP. In fact, okay, I fixed it already. That was a 20-second fix on something minor that I had never seen before. So same thing as before. The optimizers grid tie 1 are 100K. The grid tie 2 is 66. You could see that reflected. It all works very, very much the same as what I've already shown you. There's no difference here. And as far as string lengths and things like that, PV Rocket is focused on the AC side, and you really have to vet your string lengths and make sure that they're correct. I think we do have some error message that pops up now. Yeah. Maybe I'll try to force one of those messages up and show it to you. But anyway, it all works pretty much the same as what you saw before. You can even, and this is true of SolarEdge, I believe, you could still do your combiner boxes on the DC side. It all works very much the same. And the output, let me hit close on this and make sure that I've got a clean slate down here. I got one or two feeder schedules that were in the way. So if you've been watching all the videos, I've got frozen insertion points right there. I'm going to go ahead and hit print on everything and check out our output. Notice I skipped the fault current on this. It's unsupported for any system that has medium voltage in it at this time, and so it'll give you a warning for that. And here comes all the outputs. Lots of calculations at once. Did we finish? Now we're finished. Some overlapped text because we made changes from the time that we inserted the insertion points. This is the string, which is now all converted over to DC to DC converter information. And we've got all different kinds, 3 strings, 5 strings, combiner boxes, all kinds of things have been added over the course of the videos. This should all be about the same as what we did before. And let's start to look at the differences. So 6.8 amps. I don't know. The amperage is calculated differently because it's setting it changes things just a little bit. We'll leave that for another day. Let's see. That's a combiner box information right there. Let's move the array over a little bit. Now here's an example, a good example of all the information that has to go into these. Inverter 7, string 9, 18 PV1 modules, and 18 PO1 power optimizers. So there's an arrow over here, a grip point on the left that people forget is there. And you pull that out and make that look right. Let's pull this one up a little bit. Now just like on the microinverters here, it says 1 and 2. And let's just not show that. I guess the 66 only has 2 trackers in it. Something like that for the 66, and this 100 has 3 and can accommodate all the ones. But anyway, let's focus on the 1 and 2. Those go to the feeder schedule, or to the equipment schedule over here. 1 and 2, module 1, converter 1. And what I paused there for a second was I was noticing that we went equipment 1 and 2 on the array, and then we went to equipment 4 on the inverter, and then 5 on that inverter. And I was thinking, where is equipment 3? Well, equipment 3 is the combiner box. So if we scrapped all this and went back to the second box and said that the DC to DC goes, or the DC goes straight to the inverter, which I think is the more normal for Solar Edge, then we get rid of that and we can come back here and that all makes sense if you watch all the videos and use PV Rocket for a while. That'll, what I just did there will make sense. So now we lost the DC combiner box. We go straight from equipment 1 to 2, which is module and the power converter, DC to DC converter, power optimizer 1. And then we go to 2 different grid tie inverter definitions, Solar Edge Technologies, 100 kW, and then the 66.6. Then we go into aggregation panel. So when you look at the one line diagram over here, it's 1 and 2, and then it goes to 3, and then 4. And like I've shown you in the other videos, you stretch this stuff around and make it look right, and you got your output and your construction documents mostly done. And I think that's it. At least it is for power optimizers. So not much difference between that and a string inverter. And thanks for your time. So on the options tab, I've covered just about everything on other videos where it's relevant. I guess I do see a few things here. So at the very top it says string text height, and then it says 3/32 is the default, and I guess I was testing it and had 1/8 inch text height. And then PV scale works like dim scale, and as you do stringing on, really both those things only apply to the strings, I think. Yeah, it says string text height, so I think that's only for the strings. And then as you change your scale from site plan to stringing plan to this plan to that plan, it works like dim scale. So I think 120 is correct for 1 inch equals 10 feet, a engineer scale. And you change that around and you get different text heights on the strings as you string it, and also different thicknesses probably on the PV scale. And there used to be a way, let's try typing PV scale at the, oh, it is. I would have thought that'd be taken away, out. Anyway, you can access it through the command line as well. Include string length and DC voltage drop. We definitely talked about that. Ground type, we did not talk about that. So I had it checked on match the metal of the neutral. I just changed it to copper, always copper. So let me go into our fictitious 7 inverter project that we have here. and hit print feeder schedule. Oh, you know what? We were still in copper. Let me go back to the beginning. AC panel output in box number 4. Let me change these back to aluminum, which they were early in the videos. And then reprint the feeder schedule. And here you see copper phase conductors for combiner outputs, and then we have aluminum neutrals. And the first time I went through this with aluminum neutrals, we had aluminum grounds that matched the neutral size. But with that always copper checked, you're not going to get that. Okay, I'm going to erase this one line because I saw the next thing that I'm going to show you already. So right here it says aggregation panel main, and the options are always, never, or an integer. So right now we have always checked. I'm going to change it to never and hit close and go to inverter calculations and hit print the one line. Our one-line printing got a little slow in the last month. But anyway, it changes the combiner boxes to main lug only automatically. And if you put an integer in, like 6 for instance, it'll be main lug only up to and including 6. And then if you have 7 inverters going into a combiner panel, then it changes it to main breaker. So that's what that aggregation panel main meant. The DC combiner name, AC combiner name is customizable. The DC abbreviation, SB for string box, AC for combiner box, probably should be CP for combiner panel, and then change the whatever you want to do. The system prefix, we use SYS and then it's 1. I've seen other people do 1S for system 1 or one system or whatever. You would take this one away and put an S over here. Same kind of thing with strings, string prefix and string suffix. The safety distance adder we went over on another video. I like 10, 15, and 50. I'll get to this in just a second. Company name, you put yours in there. There's a few reports that start off by saying custom prepared by, and then you can put your company name in there. The plugin path, the relative job path, and the library path we cover in another video. So let's talk about this. String box configuration and calculation boxes configuration. What am I talking about? So a good example of it is on the inverter output. So you see that I'm 4 across and 2 down. I think when you first download PV Rocket and run it for the first time, you're only allowed 3 across and 2 down. And it's because if you try to put too big a box on a small computer screen, PV Rocket will crash. And we're working on an auto sizing so that this will no longer be an issue. But we ship it. The initial download defaults is 3 across, and that's because I personally have a tablet. What do you call it? A Microsoft Surface, but mine's a knockoff. And it's a super small little screen if you've ever seen those. It runs AutoCAD great. You'd be surprised. I was shocked when I first started doing it. And it's a super small screen, and so these boxes go on and on and on for me. And I've designed megawatt systems, multiple megawatts, sitting in a Starbucks with my daughter sitting across the table from me, who's now 9, watching YouTube videos on my cell phone. And I can sit there and do multiple megawatt systems. So right here on the calculations box configuration, the 20 high You probably won't have to worry about that. Let's take the 4 down to 2 just to show you how it changes the look of it. And then we go back to the inverter calcs. And we're only 2 across, and now we're 3 high. And remember, we have 7 inverters on this job, so one of them's not on here. So you click next to get to that one. And as an example, here, let's go back one. Let's make a mistake purposefully on one of them. So you go next. It'll allow you to do it, but when you want to go out of the inverter outputs altogether, it'll give you a warning. It says missing information from inverter 5, possibly others as well. So, and then you hit OK and you go back, and then you have to go back and then say, oh, I forgot to put that in. And then you're allowed to move forward. And this also, 2 wide, 3 high. Now this would cause a crash if we had more combiners, and that's kind of why we're working on it. We're auto sizing, and so we're going to auto size all these boxes to the max, the biggest size that fits for the screen that you're working on at the moment, and we'll be taking those options away from you. I'm going to put it back to 4 and 2 before I forget. And I think that's it. The reset data and the reset all data I'm going to cover in another video here in a second. Thanks. So the last thing that I can think of on PV Rocket to explain is on the options tab up here at the top. You have 2 things that say reset data and reset all data. Those are really good to create a template drawing. So the first time you go through a project, I showed you how you put the insertion points in, and if you don't put them in, when you run the output, it'll ask for them, and you drop them in wherever you want. Eventually what you're going to want to do is have those insertion points in a permanent home that they reside on, and you run through the program, and it doesn't matter what tab they're on, model space, paper space, anywhere, upside down, this way, that way, PV Rocket will seek out those insertion points and drop your output right on top of them. And I wanted to show our template of what I'm talking about. So here's an insertion point for the voltage correction factor, and guess what? It drops right into voltage correction factor. We have a nice, pretty, attractive box to enclose our stuff in. Temperature data goes into temperature data. And so when all this stuff gets populated, now it may be outside the box, it may be 3 times too long, but at least it gets you started in the right place. And the one-line diagram goes over here, and you can see combiner box locations, inverter location, interim devices, the service, feeder schedule gets up here in the right-hand corner. The system summary table falls below it. All this stuff is kind of placed around all over the place. So you do your first job and drop these in, and then you think, okay, well, I need to start making moves toward a template. Well, let me go back to the drawing, and when you, oops, well, that's fine. No, it's not fine. I'll change it. Let's look at this information, for instance, just as a for instance. So when we first came into here, this was empty. So where is this information being stored? Is it in a file that I can delete so that I get a clean slate and start scratch? No, it's embedded right into the DWG file. And so if you take an existing project and want to make that your template, it's highly advisable by PV Rocket, by me, that you erase this stuff so that you can start over again fresh. And if you reset data, let me show you that. So I hit the reset data and I go back in. Now this information is in a file, and I've shown you that. So this is still there. This is still there. But your circuit, your inverter information and everything on from here is not still there. It's gone. So if you are making a template, so that's, if you're making a template drawing, what you really want to do is hit reset all data. And then when you go in, this is still there because that's a file that follows the drawing file. So if you copy the drawing file into a new directory for a new project, that's how you get rid of this information. And now this information is gone. So I hesitated there for a second because I was thinking about the difference between reset data and reset all data. Reset all data is really for the template drawing making. So what do we have reset data that resets some of the data but not all of the data? And the simple fact is we're talking about corrupted file recovery. If you get to a point, and I hate to even talk about this because it never happens anymore, but lightning still strikes and things happen and life happens and life is unpredictable. So if you're working at 4 o'clock in the morning like I did when I was younger, and you got to get a project out and your file becomes corrupted and you're trying to run PV Rocket and it opens a box up and crashes. It's been known to happen. It doesn't happen anymore, and that's why we're publishing now. Now's the time because it's stable. But if it did happen, you could hit reset data or reset all data and put the information back in that you did and be able to recover it. Another thing that happens for corrupted files is this is the selected modules file, and I've talked about that in other videos. Something that used to happen here is something like that, where the model didn't get saved properly and it's only got the manufacturer. And the same kind of a thing, this is the module data, this is your local library. And the same kind of thing has happened in the history of PV Rocket on this, where something like that. You'll have manufacturer, model, and then all of a sudden you'll have a manufacturer with no models, and it goes on. And that might cause you a crash also. Man, that's a lot of models. And that's what oh, wait, let me go back to the options. No, that's it. So, template. Okay, another thing I wanted to show you. One last thing. If you're a plan checker, I have a file that I use a lot called plan check DWG. And what I did was I went in and put in a whole bunch of inverters, 50 of them, and a whole bunch of combiner boxes, 20 of them. And I get work where I'm asked to plan check something, and I will, without stringing anything, without doing anything on the string side, I will run PV Rocket on the AC Calcs only. And when I get to the voltage drop table, I can't get to the voltage drop table without these blocks being in there. So that's why they're there. So I describe the other people's project to PV Rocket. I get to the voltage drop box, and if they upsized things, I'll go up on that and get it to the right place and hit save, and then I get to the print, and I'm very focused on the feeder schedule and the calcs. And what I find a lot is violations of Article 250.122b. 250.122b says that if you upsize the phase conductors, and it kind of dances around the reason why you would do that, but basically it's talking about voltage drop. If you upsize the phase conductors to accommodate a voltage drop, the ground has to increase as well, proportionately. And PV Rocket does that, and it does it well. And most designers don't. And so that's where I catch 90% of my issues. I catch on that. Sometimes they're just straight undersized conductors here and there, and I see that too. But this is a nice little tool for you plan checkers. Drop something like this in and get used to getting to your feeder schedule really quick, And I'm telling you, I don't want to say how fast I do plan check, but I used to be a outsourced third-party plan reviewer for the city and county of Honolulu, Hawaii. No, I never had to go there. Everybody always asks. um, and that's about it. So that's PV Rocket. And I did leave a small handful of things out that are so detailed and into the weeds. I could not bring myself to bore you with that, thinking, when am I ever going to have to change that variable? So I didn't do everything. So obviously, if you've been watching this, this is 5 years in development and has done hundreds of megawatts of designs already done, installed, turned on, working great. If you think it's not doing something, or you think it's doing it wrong, or you think it won't do this, go to pvrocket.com. In the upper right hand corner, there's a link to our forum that me and my staff are going to manage at the start. It's a wiki forum, so as you become an expert, you can help people out too. But in the beginning, this is May 3rd, 2020, and we're about to put it on the App Store, at Autodesk, and our own website, and start to advertise. So if you think it's not doing something, ask us, and it likely is. And if it's not, that's how we add features. As I've recorded these videos, I've talked about the way that the DC combiner boxes are done. We have 3 different levels of them, and those were request after request after request as we developed. And what was another good example? I can't think of one right now, but it all comes from requests from beta users. Almost all of it. The very initial ideas came from my doing it by hand back in the day, 5 years ago. And we've come super far, a long way in 5 years. And the intent is for this to be fast, but you need to know this program. You need to know what it's asking, how it's asking it, and put it in correctly. And you need to vet every single project, the output of it. Check every single calc every single time. If I push out an update, something you checked a week ago might not be the same output that you get this week. You have to check it again and again and again. There's no substitute for your due diligence as the designer. We're sure you're going to love PV Rocket. Write us, and we're here to help you. We're going to expand the program. We already know what we're working on for the AutoCAD 2020 release in the spring of 2021. Wait, AutoCAD 2022 release, which is in the spring of 2021. We're working on that one now. If we push anything out for now, it'll be a stability issue. Somebody, as we go from 100 beta testers to 1,000 users, somebody might do something different, and we expect to have to push out some stability updates and patches. But other than that, we're going to update just like AutoCAD does once a year in the spring, match them, and move forward. So write us, go to the wiki page. Thanks for your interest in PV Rocket.